title on the blackboard.
So it's my pleasure to introduce Professor Dmitry Kaledin from HSE and Steklov to speak to us about K and D equivalence in the hyperkähler case.
Yeah. So here's the title, more or less. Thank you very much for listening. Thank you for the invitation. I'm very, very happy to be here. It's actually my first time in the country, maybe. Well, the only one here who's that late, but late and never. And so I have to apologize in advance because the story I'm going to present is kind of very old. And it's kind of almost 20 years old. And it's partly become completely standard now and partly forgotten. And I think that maybe just reminding some parts of it which are forgotten may be useful because maybe there's something more that can be done here. And so to make it topical, let's, I mean, there are various possible entry points into the story. And to make it topical, I wanted to concentrate on K and D equivalence. So let me remind you briefly what this is all about. It's something, well, as a slogan, sort of slogan, right? Roughly speaking, the slogan is that flops do not change in derived category coherent sheaves. And then these formulations actually appeared in an old preprint by Bondal and Orlov ages ago, I think in 1995, more or less. This, of course, just a slogan, and a more precise formulation appears slightly later, and it's due mostly to Kawamata, so more precisely. It's mostly due to Professor Kawamata. So let me recall that so K equivalence and D equivalence. What's a K equivalence? So if we have some X and X prime, or some field K, which are birational, then they're said to be K equivalent if now this of course considered to be a very stupid thing to do in birational geometry, but I want to assume them to be smooth. They're K equivalent if so birational means that there's some kind of birational map between them, which I can represent by a roof type diagram. And I want the canonical classes to agree. So to pull back canonical classes to X-twiddle, then it should be isomorphic. For example, just blowing up a point is not allowed because this changes the canonical class. So it's typical picture would be like two different preprint resolution of the same thing downstairs, a flop. And then, so this is definition, and then conjecture. Is that K equivalence means it happens if and only if the derived categories of coherent sheaves are the same. It's also not quite precise because I mean this is just an abstract equivalence. I didn't prescribe the equivalence, and I don't want to do it. Well, there are some kind of borderline. I mean, for example, at least this should be compatible with the restriction to the generic parts where they are identified. So there is some natural equivalence, and so one direction. More or less obvious. Well, it has to be careful, and in any case, I mean, as I said, formulation is not very precise, but more or less, if we have an equivalence of derived categories, then the canonical bundle can be recovered purely from the derived category as the so-called serve factor, which is unique. So if derived category is identified, then you can show that canonical bundles are the same also. So D implies K because this is so-called serve factor. And then the other direction is known. Yeah, you have to be careful. I mean, so not quite. Yeah. That's also true, but if you say enough additional words, then
how would you fix it to make
look, I don't really know. I have to look in the. I mean, what I want to do is go in another direction. The flop situation, which is kind of easier. Kind of, I want to look at the local statement, and let me add. One has to be careful. The good way is to impose conditional equivalence. It can be just some random equivalence. It has to be something which is. I mean, ideally, I would say that this is something given by some kind of prescribed kernel here, but we cannot prescribe the kernel. We don't know what that is. It could be delicate. It's certainly not true, for example, that you can look at the product and just look at, even if have a genuine flop, you know, like a resolution of the same thing, you look at the product and you might think that just the structure, just going to the product and then pushing down gives you the equivalence, but this only happens in very rare cases. Typically, it's not what happens. So there's some kind of more complicated kernel. And I think that imposing enough conditions on this kernel would fix it.
You're already assuming that they're birational.
Yeah, all that's from the birational.
That excludes the Borisov, Colorado.
Yeah. No, that definitely without birationality, there's not. I mean, let's say one. I mean, level 0 would be to say that this reduces to the standard equivalence on the open subset. So they have to be birational. Otherwise, the derived category is not such a strong invariant to remember that. So, right. In any case, the interest in the other direction, where I mean, general case is wide open, and I'm not even sure it's true, but many particular examples of a series of examples it is known. So the other direction. So the other direction is known, let me say, in some cases. For example, I think it's completely done in the toric case, again by Kawamoto. Again, one has to be careful. So in the toric case, it's better to work with the Lee-Mumford stacks because there could be some kind of fine stabilizers which affect derived category. So I mean, one has to be careful, but there is a formulation which is first of all true and second proved. So what I want to talk about today is another situation where the other direction is again more or less known, and I'll give you a precise statement, completely precise mathematical statement slightly later. But anyway, so another situation is the symplectic case. By the way, as I said, I mean, I assume them smooth. This is mostly for the reason of derived category, because derived categories in the non-smooth case are more difficult to study. I mean, at the time this was formulated, it was assumed that you just cannot consider non-smooth varieties from the point of view of derived categories. These days, it's known that actually you can, and maybe you should sometimes, but this becomes much more delicate, so I don't really want to go into that. I mean, this was when Bon and Orlov formulated this. This was positioned as some kind of categorical minimal model program. The idea was that things like termination of flips and flops would become easier because basically flops are supposed not to change the derived category at all, and flips are supposed to decrease it somehow. And then hopefully this will lead to termination. But I mean, this was a hope 25 years ago, which was never realized. So maybe not so useful to remember about it now because people never, and I don't think termination of flips is known even now, right? I don't know whether it's true or not, whatever. Right, so that was the original positioning. So for now, I want to restrict the symplectic case and to the smooth symplectic case, which is safer. So here's the theorem then, which is precise and true. So theorem. So assume we have two resolutions of some y. Y is a fine. So I want to go to the local situation. So back to imprecise formulation of bond and Orlov to a single flop situation. So we have some kind of a fine normal y or some k. I want it to be characteristic 0. I think that's all I want. And we have two symplectic forms. One on x, one on x prime. And symplectic is in the algebraic sense, so it's just a section of omega 2, closed, non-degenerate. I need to say closed because, as I said, I mean, this is a local situation. So these things are not really projective. I want these to be projective maps, though. Just proper, I think, is not enough. So at least we know it. And then, so we have symplectic forms, and they agree over the smooth part of y, where this is an isomorphism. They agree over smooth. Yeah. The birational, I mean, this is projective birational morphisms. Yeah. But they're secretly K-equivalent because, of course, the top power of the symplectic form trivializes the canonical bundle. So the canonical bundles are trivialized in both cases. And this excludes, for example, this means that this map is one-to-one over the smooth part of y, because the symplectic form descends downstairs. And because, I mean, you can't blow up a point. It has to be crebant. It's crebant resolution. And the forms agree. And the conclusion is that then d of x is equivalent to d of x prime. But again, I have to qualify, to be honest with you. So it's only true. Either you can say it's true locally over y with respect to the Tal topology, meaning that for every point, you know, there's a Tal neighborhood, and when you pull back, the Dirac K-equivalence. Tal topology, or quite often, I will give you slightly more precise formulation later. Quite often, people assume that there is an additional piece of structure here, which is some kind of GM action, which contracts everything to a point in y. And then in such a situation, it leads automatically to a GM action here, so the whole thing becomes GM equivariant. This is known as a conical case. And then it's true as stated. Okay, so this is the theorem, which I want to kind of explain today. I mean, I won't give you the proof, but I will give you the main construction of the proof. But in order to explain how this works, let me give you some generalities on symplectic. This is called the symplectic resolution. So there's some kind of general theory of those. Derived categories are the same. You cannot say that derived categories of x and x prime are the same in such a situation. What you can say is that, first of all, if you take a point in y, and then, I mean, number 0, you can take a formal completion near the point. Then derived categories are the same. Or you can use some kind of approximation. So you can take an Tal neighborhood of this point, and then after you pull back to the Tal neighborhood, these two guys stay symplectic because it's an Tal cover, and then derived categories are again the same. But you cannot be so brave to say that they're just the same everywhere. I'm not sure it's patches because an equivalence of derived categories is not an isomorph. I mean, it's an equivalence of categories, right? There could be some kind of Jourby, blah, blah, blah things coming in. So has to be careful. I don't know. I don't want to claim it. It's not so easy to construct example because in all examples you have this gem action actually. So in all examples you can control. Of course, there are many examples where, for example, if you have a global symplectic resolution of something, which happens, I don't know, Hilbert scheme. Well, in Hilbert scheme they are globally equivalent, but I mean there are examples, and then you can ask whether they're equivalent. It's a legitimate question, but I don't know the answer to it. Yes. Slightly better than that and slightly worse. You cannot deform to the normal cone. There is always a GM action. It will come up. Do you have an eraser? Yeah. So generalities on this symplectic singularity stuff, symplectic resolutions. So generalities on symplectic resolutions. So this whole story starts from a definition which is due to Beauville. It can be dated very precisely. It's 1999. So we have some y, which is normal. Fine. And so one says that this is a symplectic singularity. If it's equipped, so it's normal, so the smooth part is outside of convention 2. So we're supposed to have a symplectic form of the smooth part. And it's supposed to extend the resolution of singularities. In principle, this makes sense to in any characteristic, but most of the corollaries of this hold in characteristic 0. And then, so it's extends to resolution of singularities. And then kind of easy corollaries is that sort of remarks. Extends means extends as a 2 form. It doesn't have to be non-degenerate anymore. Could acquire zeros. So remarks, first of all, extends to 1 resolution means extends to any, is equivalent. To any other. Second, it's a local definition. Just yeah. Well, I can remove it, but at some point I will want to consider like global function or something. I'll forget that. I just want to emphasize I'm working in the local situation anyway. And then, so this is automatically canonical for an obvious reason, right? Because the canonical bundle upstairs has a section. And it's also rational. Well, canonical implies rational, but in this case, it's obviously rational. Well, whatever. And in fact, I think, so I've been talking, I was not current on this, but people have been working. So when I was doing this stuff 20 years ago, it was not known, but now I think it's known that the other direction is also true. So if you have a canonical singularity, then there's this extension property. And converse also true. That's why in Markov lectures yesterday we had this slightly different definition where it did not require this extension property, but required that singularity is canonical, but it's actually the same. And then so this definition 1, and then definition 2, which is very natural. This context is that to have such a symplectic singularity, then X is a symplectic resolution. If this omega, which exists on X, is actually non-degenerate everywhere. Non-degenerate. No zero, so the top power just realizes the canonical bond. Now, this clearly depends on the resolution. So if you just blow up one point, this gets destroyed. So okay. What should I first do? Examples or general properties? Okay, examples. One series of examples, just quotient singularities. We have some kind of symplectic vector space. Some finite group acting on it. Then the quotient is always a symplectic singularity. You can ask whether it has a symplectic resolutions, and so in dimension 2, of course, it does, because this is a classical dual points, it's just ID singularity. But in higher dimensions, it's a delicate question. I don't think it's completely known even now. So in dimension 2, Y has a symplectic resolution. In general, so there are necessary conditions. For example, if it were to have a symplectic resolution, then this gamma would have to be generated by what is known as quaternionic reflections. So elements whose codimension, whose fixed points subspace has codimension 2, the maximum possible. But this is definitely not sufficient. And then there are, I mean, things like that have been classified. So there has been some work analyzing which guys do have a resolution, which guys don't. I don't think it's finished even now, but there is some interesting work there. High dimension. Dimension 2, there is nothing to, I mean, this will come up here. High dimension delicate. And second, general kind of class of examples are nilpotent orbits in semi-simple Lie groups. Orbits. Like closures of nilpotent orbits, they're all like this. And actually, in this case, the existence of resolution has been completely studied by Bo-Ho-Fu. So resolutions. There's a complete, very nice theory which says that basically, if a resolution exists, if and only if it's of the form, if it's a cotangent bundle to some kind of generalized flag variety, partial flag variety, and there is a complete list of when this happens. By the work of Bo-Ho-Fu. And then another general series of examples, which is probably useful to remember, is called quiver varieties of Nakajima. Here's funny because if you look at the paper of Nakajima, there are some kind of combinatorial conditions he imposes, which he doesn't need to impose. So if you impose those conditions, then the resolution always exists. It's one of the theorems of Nakajima. under additional assumptions. And if not, it becomes interesting. For example, one example of a quiver variety which does not satisfy this assumption is the thing which comes up in a moduli space of rank 2 vector bundles on the K3 with C2 equals 4. And that does have a resolution discovered by O'Grady, which gives you a new example of hyperkähler manifold. So in that case, the singularity is actually a quiver variety, but not of the Nakajima type. And the resolution does not come from the quiver picture, but still exists. So there are like a series of examples. Maybe there are some more, but not many. So let me stop here with examples. What's funny about these definitions is that just from these pieces of data, which is not much, you can actually prove quite a lot. Turns out that already the existence of symplectic form gives you some interesting corollaries. Okay, so geometric properties of these guys. Number one, so if Y is symplectic singularity, well, one can, it's useful to look at Y as a Poisson scheme. So Y is singular, so one cannot say that it's actually symplectic. It has symplectic form on generic part, but not everywhere. But there is this notion of Poisson bracket associated with symplectic form. And that makes sense for any ring. It doesn't have to be smooth. So Y is actually naturally Poisson scheme. And then one can prove that if it were a symplectic singularity, it actually has finite number of Poisson leaves as a finite number of Poisson leaves. Effectively, it has a finite stratification, and all the strata are smooth symplectic. And these symplectic forms are not random, they all come from the same Poisson bracket on Y. In these examples, the stratification is clear. For example, here it's just stratification by the dimension of stabilizers, and for nilpotent orbits is stratification by orbits, because the closure of an orbit has orbits as small dimensional strata. And here it's also given as part of the data. And then it can also have good transversal slices. So I won't need this. I don't give you a precise definition, but basically if you have a point in Y, as I said, it lies in some stratum, which is smooth symplectic, but you can also, at least in the formal neighborhood of this point, you can find a transversal slice, which is also symplectic singularity, and the whole thing decomposes into products. Good transversal slices. Second, Y always has a GM action that acts non-trivial on the form, that acts on the form of some kind of weight which is not zero. Acts non-trivially on this omega. It has to be qualified. So what? It's not quite true the way I stated. So this is a very local statement. So you choose a point here, and you take the formal completion near the point. Just look at the picture near formal completion of the point. And then it turns out that you can always find the GM action there, which acts on the Poisson structure on the form or some kind of non-trivial weight, which implies in particular that the action is non-trivial itself. It cannot be just constant, which is weird because in the world of singularities, I mean, typically a singular scheme would have no GM action. I mean, GM action algebraically it's a grading. I mean, why would you expect a random ring to have a grading? So this one does. The problem which is still open is that we cannot prove that this action is positive weight. There's some kind of GM action, some kind of grading. But ideally, in all examples, we know that it's actually positive weight. I mean, weight from 0 and in one direction, but in general, we cannot prove it. So cannot. Because, I mean, we cannot prove it for a good reason. It's not true in general. There could be many GM actions. So the correct statement should be that if you have one, you can correct it so it becomes positive weight. It's not clear how to prove that. That's positive weights. In practice, people impose this. So they call it conical. They call it singularity conical. There's some kind of GM action which contracts everything to a point here, which is the same as having positive weight. And then it's easy to see that if you have, well, it's not quite obvious, but it's not difficult to show that if you have a symplectic or in fact any Crepin resolution, then a GM action automatically lives there. So the whole picture becomes GM equivariant. And this is very useful because this gives you some kind of compactness. So this allows you to prove stuff. So answering Dan's question, normal cone wouldn't work because that's the wrong GM action. It destroys the Poisson break. I mean, destroys the, you won't have a smooth resolution. So it's not the action you want. But in practice, we expect there to be an action we want. We can prove it in general, but in all examples, it's a given. Here, this action is just, dilation of the vector space. Okay, what else? So this is geometry for symplectic singularities. Then also, if you have a resolution now, it's automatically semi-small. That is dimension of x cross x over y. It's the same as dimension of x. So you cannot have, say, a divisor contracting to a point. What else? Conical set. And there are some homological properties. So you can look at the homology of a resolution. And then you can prove that, say, homology of rational coefficients carries a Hodge structure, of course. Now it has to be characteristic 0, but let's tacitly assume I am there. And so this thing is actually pure Hodge state. And in fact, more. You can actually show that this is generated by classes of algebraic cycles. I'm stating this separately because this is an easier statement. This is harder. Still true. By classes of algebraic cycles. So cohomologically, this thing behaves as if it were very, very, very much rational. Like, for example, something like a flag variety, which just has a stratification by affine spaces, right? You can claim the same in general, but cohomologically it behaves as if it were like that. Yes. No.
If Y was just a smooth symplectic,
it would have no symplectic resolution.
that would be identical.
Correct. Conical. Either conical or in the formal neighborhood of a point on Y. Yes. Also. No, this is true actually always, but here I want X conical. Or complete near Y. You're absolutely correct. It can be, yeah. Well, it's not a divisor. Yeah. But the whole homology is contractible to this exceptional, to the 0 fiber. And this is pure Hodge state. No, I mean, the special fiber, I mean, one example I forgot here, although it's covered by this sort of, is a Hilbert scheme of points on C2. And in that case, the the special fiber would be what is known as a punctual Hilbert scheme. And it actually has non-trivial geometry. Already for 3 points, it's some kind of, I think it's one of the Hirzebruch surface, I forgot which form maybe, with one of the sections contracted. So singular, it actually has quite non-trivial topology. But cohomologically, it's trivial. All right. And so now let me explain. So this statement which I just erased about derived categories, I could reinstate it, but in fact, I want to show the statement which you actually prove. And for that, I need one more notion, which is from the world of derived categories. So it's a general thing. So definition. Assume we have some y, which is affine, normal. And let's, for simplicity, let's say Gorenstein. Then a non-commutative Crepant resolution. Y is the following thing. So it's a sheaf of Y algebras. So it's just a coherent sheaf on Y, which has an algebra structure such that generically it's just a matrix algebra. Generically on Y, meaning outside the singularities. Algebra. And then A has fine global dimension. Well, I mean, this is an affine situation. So I'm saying a sheaf of algebras, I might as well just take the global sections. It's a non-commutative ring. And I want this to have a finite global dimension. And be Gorenstein. I mean, Gorenstein makes sense for non-commutative rings also. The idea here is the following. So in the non-commutative situation, when we only care, actually, we don't care about rings, we care about categories of modules of a ring. And in that setting, a matrix algebra is the same as a field, because the Morita equivalence of the models are the same. So this, roughly speaking, says that this R is a resolution. So there's kind of birational map. And finite global dimension is taken to mean that this thing is smooth in some sense. Because, of course, for commutative rings, by Serre's criterion, we know that it's smooth if we don't leave it has finite global dimension. So an example of such a thing is precisely what Evgeny already mentioned. It occurs in the quotient singularity case, and it's the stacky quotient. So, I can write it down, but I will screw it up. But basically, I mean, categorically, Gorenstein measures the Serre functor, which is trivial. Serre functor is a bimodule. So repeat that literally.
Global dimension doesn't imply both.
Probably should be probably part of the definition, I think. No, it doesn't. I don't think it. Just to be safe, I mean, let's impose both. No, I don't think it does, but keep an example for now. Okay, so no. So V mod gamma. So algebraically, Y is this. And then this is also algebraically, this is the spectrum of the ring of invariants, right? You take the symmetric algebra of V dual, take gamma invariants. And then it always, I mean, this has nothing to do with the symplectic story. This always has a resolution in this sense. Assume that gamma is in SL, so fix the volume form. Always have NC resolution, which is the following. So I need a ring, right? So instead of taking invariants, I take the known as mesh product. Or if you want a twisted group algebra. So just something which is as a vector space is generated by elements like this, where A is a polynomial, gamma is an element in the group, and then the product is that the A gamma times A prime gamma prime is A prime, and then you have to act. So A, and then you have to act by gamma on A prime, and then it's gamma gamma prime. I think actually that answers your question. So I think if the group is not in a cell, does not fix the determinant, then this thing is maybe not it's the other way around. You said that Gorenstein applies for finite global dimension, right? Yeah. All right. So if gamma is not on a cell, then this won't be Gorenstein, and this won't be Gorenstein. So it might still be Krepet in some sense, but I don't want to go into that sense because for me, I want to stick to a situation where everything is living symplectic, so it's all fine. All right. And this is always fine global dimension on characteristic 0. Even if we don't have a resolution, Krepet resolution of this in the genuine geometric sense, or even the symplectic one, you always have this guy. And then the general theorem is that this is what always happens. So I mean, we don't know. One could be so brave as to conjecture that every symplectic resolution has a non-commutative resolution. There are no counterexamples. In fact, it looks plausible, but hard. But what one can actually prove is that if you do have a geometric resolution, symmetric resolution, then you have such a thing also. So the precise statement is as follows. Yeah. I mean, it's probably Krepent even if you don't oppose this, but that depends on the definition of Krepent. Just if you say this, then it's Krepent in the most usual sense. Everything's Gorenstein. Right. So the statement is as follows then. Assume we have a symplectic resolution. By the way, a trivial remark. I mean, I want this to be affine, which means that actually the data here is X. Y can be recovered uniquely from X as just a spectrum of the ring of global functions. So this is the data. Then Y admits, and here, unless I'm totally mistaken, one can even say this without restricting to the conical case or whatever. Non-commutative. No, let's say conical just to be safe. I don't remember exactly. Fairpoint resolution A such that, as I said, we're not interested in rings, we're interested in models of rings and categories of those models and derived categories of those models. And in this case, this thing is equivalent to X. The derived category of X is equivalent to the derived category of modules over this R, which is just the algebra of normal sections of this A. In particular, if we are in such a situation, then this claims that there is some kind of A which gives you a resolution. And in fact, so this like theorem 1 and theorem 2 says that if Y happens to be a quotient singularity, one can actually choose this A to be exactly this. Is known as K-equivalence. So this statement by itself prescribes you quite a lot about the topology of the resolutions. For example, you can compute cohomology directly because so there's quotient homology, which is invariant to the derived category, and from this equivalence you can compute this on this stack, and that is well known. And at the end of the day, you get what is prescribed by Mackay correspondence. I mean, that was known before this equivalence, but it actually packages that itself in quite a nice way. But the theorem is that even in the general situation where you have no control over Y, and this Y can be, well, it's not too bad, but still, so it doesn't have to be Q-Gorenstein, for example. Typically, it is not Q-Gorenstein because typically you get some kind of divisors contracting to something. They cannot contract the point because this is semi-small, but they might as well might very well contract to something of dimension 2 here. I mean, there could be many. I mean, another typical example of such a situation you should keep in mind is just T star of the projective space, for example. So this contracts to the quadric. So this is also an example of symplectic resolution. It's actually even well semi-small and but small in the sense of birational geometry, meaning that Picard drops. So you don't know much about this Y algebraically, but we know that it has a non-commutative resolution. And this thing about D-equivalence, which I mentioned, which I stated before, is actually proved exactly using theorem 1. So you do this, and then you just observe that the construction of this A is such that if you have two different resolutions, you can compare the algebras and see that they're basically they're the same. So that's how I prove that. And
every two NCCRs are derived. So this is another limitation.
no, you I don't think you can. At least I can't. No, what I can do is specifically in this situation. Actually, it's a very good question. Maybe it should be possible to do it, but the current proof would not work because it really works by explicit construction. You start with an X, you construct by some kind of procedure, which I will explain in a moment, construct such an A. But then you see A at the end of the day is just a sheaf of on an affine variety, normal affine variety, and it's not such a bad sheaf. Basically, it's you could show that it's enough to compare it outside of high codimension. Just because of that, basically, if two non-commutative resolutions agree outside of some locus, they agree. And that you can do just look at the construction, basically. But the construction, as you will see in a moment, is actually not unique. I mean, there are choices there. And we cannot even compare what happens if you do different choices.
same with Vandenberg.
Yes. For him, I mean, Vandenberg, of course, started this whole business, but he worked in a situation where you have relative dimension 1, which makes it somewhat easier. So some things happen which you cannot hope to have in higher dimensions. And there he explicitly, there is a very beautiful picture exactly for three-dimensional flops. Which is actually a long story. I mean, it has been explored by people like Wims and is being explored even now. There's a long story, pure algebraic story, which gives you a lot about pagodas and all that stuff. Yeah, but only relative dimension 1, unfortunately. Okay, so let me explain the main steps in doing this. So the strategy is like this. It's really weird. Step 1, reduce the positive characteristic. No, it gets worse. Step 2, do a deformation quantization there. Quantization. Then leave it back and then enjoy. Really weird story. So what happens is the following. So, I mean, what's a deformation quantization? Something you can state for any symplectic stuff anywhere. So definition, a quantization. Is just a sheaf of associative, not necessarily commutative algebras. Over, well, our base field plus formal power series on one formal variable, flat. Flat meaning no H torsion. Flat complete. Well, deformation, right? Sometimes in the literature, people write that this is just a star product on functions, but that's not the correct definition because it could be a non-trivial sheaf extension in the Zariski topology. And such that an equivalent isomorphism so modulo H, it should be identified with just a sheaf of functions. It's all in the Zariski topology. Zariski topology is good enough for this. So once you do this, you can look at, so it's commutative modulo H, you can ask at the first, at the commutator, and then the commutators, of course, can be written as you take two functions, you take some liftings to sections of OH. You can look at the commutator, it has to be divisible by H. And then you look at the leading term. And you see very soon that this only depends on the reductions of F of G mod H. So this gives you some kind of additional structure, which is a Poisson bracket. It's a Poisson bracket. So any quantization first order gives you a Poisson bracket. And typically people prescribe the Poisson bracket and want to find a quantization which realizes this particular Poisson bracket. In particular, we're in a symplectic case, so there is a Poisson bracket given by the form, and they want that one. But this makes sense of any field in any characteristic. The standard example is, of course, Heisenberg algebra. I mean, the algebra is called Heisenberg Lie algebra, and the corresponding algebra is called the Weil algebra. Just, you know, some generators, and then Heisenberg commutation relations. Plus some other obvious relations like X is commute, Y commute. I'm not write them down. This is the important one. Now, weird feature of characteristic zero, of characteristic P is that if you look at what happens in characteristic P, then this algebra suddenly acquires a huge center. In characteristic zero, this is a simple algebra. It has no center except for the constants, and it has very few modules. P, this, let me call it A, has a huge center. basically all the p powers are central. So the center is as large as the algebra itself, basically. And so you can look at deformation quantization problem in characteristic zero, and there you can prove that they exist under some chronological assumptions on X, and actually can be classified. So it's a nice story. But what's interesting that you can also look in positive characteristic, and there also you can prove something. So you don't want arbitrary quantization characteristic P, but you want those where this center exists. So the things which also have similar behavior to the standard one. And so definition, let's say K is something of characteristic P and perfect. Perfect means that the Frobenius is bijective. Definition, Frobenius constant quantization is what? So we have some kind of quantization of, we have some kind of Poisson variety, we have some kind of quantization. I can consider OH mod H, and this is by definition identified with OX. I can actually go slightly, there is something in between. I can first take out p powers of H, but keep all the p minus 1, p minus 2, I mean, keep the first several terms. So here I have the subsheaf formed by p powers. And this abstractly isomorphic to OX, just by, they identified by the Frobenius map. X goes to the X of P. And then if you look at it, surprisingly, this correspondence X goes to the X to the power P is actually an additive map from this guy here. So this algebra is not commutative anymore, but it's kind of non-commutative in a controlled way. If you write down several iterated commutators, at some point it becomes 0. And this is enough to show that this map is still additive. So there is a map here. And then what you want this to lift somehow some kind of map from this guy to the center of this. So this is a central map. So this is called Frobenius constant quantization. And then a theorem says that, theorem of Bezrukovnikov and me, says that those things exist. So if H has no coherent homology, then Frobenius constant quantizations exist and are actually canonically classified by elements in a group, so correspond to. So the group which classifies them is as follows. It's first a talc homology of X of coefficients. You take the invertible functions and you mod out by p powers. And of course, this group can be described. I mean, there's a Kummer long exact Kummer short exact sequence. So there is a long exact sequence of homology. So this is something which maps into the p torsion part of the Brouwer group. And the kernel is Picard mod P. Symplectic. No, actually, no, sorry. Symplectic, but there is more. Right. Characteristic zero at least local analytic topology, there is double theorem. All symplectic forms are the same. Characteristic P is not true because there is this Cartier isomorphism, which is local invariant on symplectic form. So you want this omega to be locally exact, which is not automatic in characteristic P at all, it's condition. And then this cohomology assumptions. Right. So the point here is this. Which part? Yeah. Correspond to classes. Yeah. Frobenius constant quantization, like this. I'm sorry, exist, and actually they are classified. There's a canonical parameterization by elements in this group. And this group, of course, fits into, so to see what this group is, it fits into a short exact sequence like this. So this part is not very useful to us, but the useful thing is that you can twist by line bundles. So there's this freedom, this flexibility of choosing something like that. Prescribe Poisson bracket. And also I want, so the Frobenius constant is also data. So there's a data of this. So a posteriori, they would have this center, but they would actually all have center, which is also functions on X, in fact. I mean, Pth powers, but as I said, they're abstractly identified by the Frobenius map. There's a central map. It maps this a commutative ring. I want a map from this guy to the center of this algebra. Central map to me means a map which goes into the center of this ring homomorphism, first of all, but more than that, it actually goes into the center. And then, of course, I'm totally out of time. So just in one sentence, so you do this, you reduce mod P, you do this, and this gives you an algebra with a large center now. It's not quite a matrix algebra. Generically, it's not the my algebra, but it's enough to lift it back to characteristic 0. And then if you choose P appropriately, I mean, P is yours. You can choose P in any way you want. So if P is large enough, then, of course, the Brouwer group in characteristic 0 is, you can bound the torsion, so you can arrange it so that the my algebra lifts to something which is split. It becomes a matrix algebra generically and gives you your non-commutative resolution at the end of the day. You start with functions. You do the quantization. This gives you already an my algebra because it has it now you do this kind of quantization which has a center, and it's very easy to show that generically of the center it will be an my algebra. It will not be a split at the my algebra. In fact, in our paper with Bezirkov, there is a mistake in the end which says it should be split. It's not. And these days you can also, there is a paper by Bogdanov and Vologodsky where they actually compute the Brouwer class of this as my algebra, and it turns out to be a very delicate thing to do, but they do it. But in any case, it's my algebra, so it has reasonable deformation theory. And then you can lift it back to characteristic 0, and after that it becomes split if P is large enough, and you get your non-commutative resolution. And then to show that this is not, so you get some kind of algebra. To show that it's actually non-commutative resolution, you have to show that something generates the derived category of X. And for that, the statement is roughly like this. So you look at this additional parameter here, and you show that there's only a finite number of bad values of parameter. And this finite number does not depend on P. And so you just choose P large enough, and it works. And the result, as you can imagine, is completely uncontrollable. And this has been around for, I don't know, 17 years. There's only one case where people actually managed to do the whole procedure explicitly. And this is the so-called hypertoric case. Because on that case, at the end of the day, the whole derived category generated by line bundles. So you can actually do this computation. It's Ben Webster and collaborators. I forgot the full list, and we don't even know how it depends on P. So different P a priori. So the only example where it's easy to do explicitly is T star of P1. And in that case, at the end of the day, you get some kind of E which generates the derived category. And typically it will be O with some multiplicity plus O1 of multiplicity, say P minus A. A is an element corresponding to this choice in PCAR. You see that if A is 0, then this is a bad situation because this thing does not generate a whole category, but typically it does. And the only thing that depends on P or on A is the multiplicity. It's generated line bundle is the sum of several objects, different multiplicities. Of course, we expect the picture to be the same in the general case, but we don't know. Okay, I'm 3 minutes over time, so let me take 1 second and state 2 things which should be possible to do. One should be possible. It should be possible to do this construction more explicitly, at least in the case of like T star of G mod P and so on, and to get quantum groups at roots of unity. The remark to this effect is already in the paper, but I mean somehow people. I think it should be possible to do it. It's interesting to do it. And another thing it should be possible to do, as I said, you can hope that all symplectic singularities have symplectic resolutions in those non-commutative sense. This may be too much, but one specific example where it's very hopeful is moduli spaces of vector bundles on K3, which start the whole business. There we know that there is one specific situation where you have an honest symplectic resolution, geometric symplectic resolution, that gives you O'Grady's examples of hyperkähler manifolds. And there's a theorem that you cannot, so all the others don't have such a resolution. You can prove it, but I'm pretty sure they must have non-commutative ones. And this, I think, something which should be explored. Okay, I'm very sorry for all this, and yeah, thank you for your attention.
Questions?
Yeah.
I may have missed this. What makes the derived category of X equivalent to the derived category of R?
Okay. Roughly speaking, it's like this. So you do something by quantization. So at the end of the day, you get some mathematical algebra on X and characteristic P, and models over that are equivalent to models over Y. And then the question becomes whether this taking global sections is an equivalence or not. You can measure the failure of this gate to be an equivalence. So that going down and then back up is represented by a certain kernel on X cross X. So there's this kernel. And then you don't know whether it's 0 or not. I mean, there's a part which is a diagonal, which is what you want, and then there's the rest which you want to kill off. And the play is with this flexibility here. You don't even need the full PCAR. You choose just some line bundle, some ample line bundle, and you take multiples of this line bundle and twist the quantization by this. And just numerically, they show that all the bad components of this kernel can occur only in a finitely many number of parameters here. And the number of the parameters is not does not depend on P. So it's a very, very non-explicit argument. Yeah.
This condition of higher cohomology vanishing of O,
Uh-huh.
that cannot be a global statement because, right? I mean, you can never have like a global symplectic thing because
Of
and
course.
the top. Okay.
Oh, this is a very local construction.
Right.
And I don't know whether it's possible to relax this somehow. This is because you get some kind of Jerby deformations, blah,
Sure.
blah, blah.
Sure.
So it's very delicate. Yeah. I am. I should have, yeah. No, this whole story has very, very nice deformation properties. Meaning that when you have a symplectic resolution, you can deform the whole picture so that the map becomes an isomorph, which is very weird, right? Downstairs you have something which was affine but singular. Upstairs you have something which is smooth but not affine, and then they become the same and affine. Looks weird, but you should think about T star of Pn and then deformation to a twisted cotangent bundle, which goes to quadric. So this whole story, yes, I mean, it's pretty much compatible with deformation. And these parameters here are also related to parameters of the symplectic deformation. So that story works very nicely.
Is there any kind of, I guess, étal local statement that maybe all symplectic resolutions look like that first example? Because it seems so fundamental that.
First example, what?
If you have a symplectic vector space and you take a quotient,
Ah.
quotient by a symplectic.
There is a vague hope that all symplectic singularities are somehow related to groups, but that's the most we can say. And I mean, Okounkov, who likes to sell things, he says that, symplectic relations are like Lie algebra in the 21st century, in whatever sense. The point is, no, I wouldn't be even so brave as to suggest a statement. As an example, so there is this well-known famous theorem of Mori that when you have a tangent bundle which is ample, then the thing must be Pn. Geometrically, this means that T star of X is the symplectic resolution of an isolated singularity. And there is a conjecture which attributed, I don't know, like Dumail maybe, or Campanel, Peternel, somebody. Nobody is brave enough to, which says that if T star of M, if the tangent bundle is ample, no, not ample, but nef and big, or geometrically, if T star of M is a resolution of something, but not necessarily the singularity, then it must be G mod P. So everybody believes it, but it's completely impossible to it's really very hard. So the answer to your question is that probably it is true, but it's of the level of hardness even bigger than that one. So for now, it's hopeless, I think.